So you get a graph, and you get a continuous differentiable function. Something pretty straightforward, no need for that much detail. Now, first thing you do is you estimate one of the x plots. And you find its corresponding y value, right? So, doing that, you draw the line tangent to that. So I'm just going to draw a line that's not actually tangent to this graph, but let's assume it is. Draw a line tangent to that one, and it brings you closer to the actual root. What you do from that point is this new root that you have, you find the x value, draw another tangent line, and that brings you closer to this root. Now with these graphs, you simply repeat that process until you get a nice estimate. That is Newton's method in the graph form. My group mates will show you how to do it mathematically. However, there is one crucial point. In order to find a root, you must know that it has a root in the first place, which is one of the key points in Newton's method, is that how do you even know it has a root? That is due to the intermediate value theorem. So the intermediate value theorem states that if you have a curve such as y equals f of x, right? And it is continuous between interval a, b. Right? Then there will be a number at w that is in between f of a and f of b. So that'll look something like this. You have intervals a, intervals b, f of b, f of a, and w. F of b, and f of a. Somewhere in between there, there will be a value that corresponds. Now, we know that this is possible for our function because any function that is a polynomial is both differentiable and continuous, which are the parameters to be able to do the intermediate value theorem. Our function, being this, is a polynomial, thus both differentiable and continuous. So, Newton's method applies.
Hey everyone, this is Max. I'm going to try to keep it short and simple today. My question is 2a. 2a states, use it, meaning Newton's method, to find the root of x cubed minus x equal to 1, correct to the 8 decimal places if x of 1 is equal to 1. X of 1 is equal to 1 is an initial approximation. I'm going to add that on the board because it's very important. And it'll help us going forward with this problem. As you know, Newton's method is x of n plus 1 equal to x of n minus f of xn divided by f prime of xn. In this case, we were given a root. This root was x cubed minus x equals 1, as you may remember. So to put in the simpler terms, I could find f of xn, which would be just x cubed minus x minus 1. But below, it's going to be a little different, because this is going to be the derivative of f of xn. And that's going to be 3x squared minus 1. Remember, these x's stand for x of n, so I'll add it in. I won't add it in because I'm not trying to make it confusing, but let's continue. All right, knowing that x of 1 is equal to 1, I could start off right away and use Newton's method. All right, here we go. X of 1 plus 1. So if you notice, we're solving for x of 2. It's equal to x of 1 minus f of xn. In this case, it's f of x1. And that has an output of 1. So it's going to be 1 cubed minus 1 over 3 times 1 squared minus 1. As you can see, this marker is running out of ink, so I'm going to move over to this. All right. Now I have x of 2 is equal to, remember, it's an output of 1, so I'm just going to put it right here. That's going to be 1 minus 1 is 0, minus 1, negative 1, over 1 squared times 3 is 3, minus 1, 2. With that, we're subtracting a negative. That's going to become addition. So x of 2 is equal to 1.5. So right now, as you can see, we don't have 8 decimal places. So I'm going to have to keep on going forward. It's good to do a couple of iterations to see how everything's done and how once I find the second iteration, which will be x of 3, there's going to be a lot more decimal places that I'm going to have to look at and compare with other iterations. So I know x of 2 is equal to 1.5. Now I'm going to solve for x of 3. X of 2 plus 1 equals x of 2 minus, remember, we're dealing with the output. So the output of x of 2 is equal to 1.5. So we're going to put it in the f of x of n and f prime of x of n. So it's going to be 1.5 cubed minus 1.5 minus 1 over 3 times 1.5 squared minus 1. Now I could go through every step, but I really don't think that's the best idea. So right now, I'm just going to skip a couple steps, and I'm going to bring us to x of 3 is equal to 1.5. I'll write it anyways. 0.875 over 5.75. X of 3 ends up being 1.347826 0.870. So as you can see, it's a bit different from x of 2. We're right now 1, 2, 3, 4, 5, 6, 7, 8, 9. I don't really need the 0, but it's good to make sure that we have everything intact, and yeah, we'll try to deal with only 8 decimal places at the moment. But all right. And I'll quickly go through x of 4, and then I think you'll have the hang of it, and then I can get to the end of this. So x of 4 is going to be x of 3 plus 1 equals x of 3 minus that put into f of x of n and f prime of x of n. And this is going to be a lot of junk. So here I'm actually going to skip some steps. but I'll first write it out in a simpler form. F prime of x3. Remember, we're just putting that into here and here. Then I'm going to get x of 4 is equal to 1.347826087 minus a lot of junk. This is a lot to write down. 0.0226256881. Get the gist of it? X of 4 is going to be equal to 1.325200399. So we found x of 4. Now I could go on all day, but it's going to take another 10 to 20 minutes, and I don't really want to keep you waiting. So we know this right here is the third iteration. Knowing that, I put this in the Excel, so a spreadsheet with the help of Marissa and my group members, Ian and Omari. And we found that the 5th and 6th iterations matched. So this means x of 6 was equal to 1.324717,952. And x of 7 was also equal to the same thing. And from there on, it continued to be the same 8 decimals that matched up with each other. So, as I said before, it took 6 iterations to match up, because this is the 5th. And this is the 6th iteration and the first match. So at the end of the day, we found that it took 6 iterations, and it didn't take a whole lot of time, but I took a while writing it on the board. But at the end of the day, you can see, like, as we deal with more decimal places, it gets longer and longer. And so when Omari deals with 2b, which is x of 1 is equal to 0.6, you're going to see that it's going to get a lot more like a bunch of junk like this, where it doesn't match up, and there's going to be a lot more iterations to deal with. All right, thanks.
For this part, 2b, we now have to calculate with Newton's method using our new root of x of 1 equals 0.6. I may notice that this is less as compared to our first root, which will be explained in the later part as to why it's important to make sure that you have an accurate guess. So, for this, we have to plug it into the equation like we did into A. F of x of 1 equals f of x of 1 equals x of 1 squared minus x of 1 minus 1. And we plug it in, we have 0.216, which is 0.6 cubed minus 0.6 minus 1. When you evaluate it out, you come out to out to negative 1.384. Now, even though we have to calculate the numbers up to 8 decimals, that comes in later. For now, though, let's move on to calculating our new root in our prime of our function, which is 3x squared minus 1. Now, if we plug it into here, we get 0.3, which is 1.08 minus 1, which is 0.08. We have this as our f, and this as our f prime. Now that we have our x of 1, our f x of 1, and f prime of x of 1, we can finally plug it into this equation so that we can find our x of 2, or as it says in the equation, our x of xn plus 1, which goes into that, because 1 plus 1 equals 2, and we get into that. Now, we have our x of 1 minus f of x of 1 divided by f prime of x of 1. Now, when we plug it in, and you are welcome to equate it out yourself. We have an x of 2 equals 17.9. Now the thing with this is that as opposed to our first root where we have x of 1 equals 1, we have to keep equating it through until we get to our 8 repeating decimals. And we find that it is right when we reach x of 12 that when we plug that into our equation again, when we get to x of 13, that's when we find our 8 repeating decimals. And we are going to equate it out so that you know for sure that is correct. It's always nice to check so that you know what you're doing and you have the correct calculations. Plug it into our first function. For the sake of the amount of decimals that we have, and so that we don't take too much space on the board, we're just going to go ahead and have it as this. Plug it in. We have 2.32471814 minus our x of 12, which is 1.3247179992 minus 1. Now this comes out to 0.000000148 minus 1.000000148 minus 1 is 0.000000148, which is our function. Now, plug in the same thing for our f prime of that. We have 3x squared minus 1. Plug that in. 3 times 1.24 minus 1. Is 5.26463.3275 minus 1, which can be easily equated to 4 point da 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 da. Now that we have what our function and prime function would be had we plug in 0.6, we now plug it back into our Newton's method. X of 12 minus f of x of 12 divided by f prime of x of 12. Come over here. We have minus what we had from our first, which is 0.000000148 divided by 4.264633275, which comes out to 6 divided by comes out to a decimal, which will be easier to just leave as it is. But when we subtract it from 1.342717992, we get 1 point. We subtract it from here, we have x of 13 equals 1.324711796. There was a 957, but since we're going to the same 8 decimals, you round off. And if you equate it further, you'll find that this will be the repeating 8 decimals with the 13th, 14th, 15th, 16th, and so on iterations. And that concludes it for our part 2b. Alright, this part 2c, we now calculate our Newton's method when our root is now 0.57. Now, just as the previous parts, we plug it into our f of x of n and f prime x of n, so that we can plug it back into our Newton's method and find our x of n plus 1. We plug it into our function, have our f of 0.57 as negative 1.38480700. That is our f. Now, when we find our f prime of this, we have f of 0.57. 3 times 7 squared minus 1. We have our f prime of it to be 0.0253000. 8. Now, these are messy numbers, and obviously it take a whole lot of space just to deal with these numbers in the Newton's method. So we're going to sort of streamline that process so that we can give you the answer. We're finding the x of 2, which is x sub 1. Yeah, x sub 1 minus f of x of 1 over f prime of x of 1. Plug it in, we get 0.57 minus what we have for this, which is negative 1.384807 divided by negative 0.0253 and when we divide those two numbers, we have we have 54.735454 minus 0.57, which totals out to negative 54.165454555. This is our x of 2. Now, compared to the other two that we had, where it was x of 1 equals 1 and x of 1 equals 0.6, this one will take a lot more iterations to take. So much more that it could take up the entirety of this video, honestly. However, for streamline purposes, we're going to go all the way down to where it hits its iteration, which is x sub 34 equals x sub 34 of this number is where we hit our 8 repeating decimals. But to make sure that we have our 8 repeating decimals, we are going to equate it out. obviously I'm substituting our actual number as x sub 34 so that you don't have to deal with all those nasty numbers on the board at one time. When we equate it out, for the f, we have 0.047. 0.002. And as for our f prime of x sub 34, we come out to 4.27. We have our f prime of x sub 34 and our f of x sub 34. Now, of course, we have to plug it back into here, which will mean that we have x sub 35 equals 1.32582792244 minus our f of x sub 34 divided by our f prime of x sub 34. Equating this out comes out to 1.3. That is why x sub 35 is. And if we were going further, you find that x sub 36 is, let's see, nine six. Same goes for x sub 37, x sub 38, and so on. Now, as I mentioned in the beginning, an important thing to notice is that our root this time was 0.57. And as you saw with the iterations we had to go all the way up to x sub 34 for us. Actually, no. It wasn't until x sub 35 that we reached our repeating decimals. So as opposed to x sub 1 of 0.6 and x sub 1 of 1, this takes about 13 iterations, while this takes up about 6. X sub 1 of 0.57, however, totals out to 35 iterations before we hit our 8 repeating decimals. The reason why is because, as I stated as well in the beginning, we are way further than our initial estimation. And the further you are, the more you have to calculate so that you can find a more precise number, or to get to your 8 repeating decimals. And that concludes it for part 2C.
Is Newton's method actually efficient, and when should it be used or not be used? Well, yeah, short answer, Newton's method is pretty efficient. If you have a simple graph, something like this, then yeah, you make an estimation, you take the tangent line. This estimation now brings you closer and closer to actually finding what you're looking for. However, there are times where Newton's method is not very efficient. For example, let's try a cubic function. If your cubic function looks something like this, then no, Newton's method isn't going to be very efficient for a couple of reasons. One, if you start off too far away, you can end up losing yourself forever in the equation. For example, if I choose here, and I start with this tangent line, it'll bring me here, and I could end up going right back to where I started and be in a never-ending cycle. Another issue that could happen is you never want to pick somewhere where the instantaneous rate of change is going to be 0. If the instantaneous rate of change is going to be 0, for example, there, that means that the tangent line also has no slope, and you will never end up finding the root that you were looking for. In conclusion, Newton's method is pretty useful. It's just you have to be aware of some of the errors that you're capable of making when using this method. And also, it's pretty much obsolete nowadays since we do have access to graphing calculators and no longer need to estimate or narrow down the root. We can actually just punch in the numbers and get the root exactly for what it is.